Newton 2021. No.
All right, so our last exercise
I think so.
is applications to physical situations. And it's going to require a little bit of talk that's going to sound a lot like physics. So we're going to go through a few basic physics concepts here at the beginning. So first of all, Newton's law and the units of force. 1 Newton can be written as 1 with a capital N, N for Newton, is the force required to accelerate a body at a rate of 1 meter per second. Newton's second law, we'll be using that a lot, says that the force acting on a body is equal to the mass times the acceleration, m for mass and a for acceleration in meters per second squared. Then the sum of all the forces acting on the body has a magnitude of F equals ma newtons and acts in the same direction as the acceleration. 1 kilogram weight is the downward force due to gravity on a mass of 1 kilogram at the Earth's surface. Technically, you guys have probably had this discussion in physics, that the force is actually slightly different depending on your where you are on the Earth and how far you are above sea level. Okay, but we're just going to stick to 1 kilogram on the Earth's surface.
So we're saying that the gravity changes from the bottom floor of the to the top floor.
Yeah.
If you measure it.
Yeah, but we're just going to keep it simple, and we're going to stick with acceleration due to gravity at the Earth's surface, which has the symbol G for gravity, and its approximate value is 9.8 meters per second. In some questions, it will ask you to round that to 10.
That is the first.
Yes, if you're putting in direction, depends on the question which way we're going with that. All right, 1 Newton is therefore about 1/10 of a kilogram weight. So if you're thinking about a 100-gram apple sitting in your hand, that is 1/10 of a kilogram, 100 grams. That is what 1 Newton's force would feel like. Okay, so here is a bunch of practical, hopefully a bit more practical questions. Most of these beginning ones asks us to do the questions in 2 ways. It asks us to do it with basically trigonometry techniques, and then it asks us to use vectors, and it will involve projections. Okay, so question number 1. I walk 30 kilometers in a direction north 40 degrees east. Find how far north I have gone. So it says using a map of my journey, and I'm going to be using normal trigonometry to help me solve that for part A. So here is my diagram. Always like to have a diagram. I am traveling at north, so that's going to be my north line there. North 40 degrees towards the east. So there'd be a 40-degree angle in there, heading towards the east. And that is for a distance of 30 kilometers. And I want to find how far north I have gone. So I'm simply going to go dotted line across there to the north. And I'm going to find the length of, I might call this O, so I can make that the length ON. Okay, so using right-angled triangles, SOHCAHTOA stuff, I would be wanting to find the adjacent side, and I know the hypotenuse is 30, so I'm going to be using cos. So cos of 40 equals adjacent, which I'm going to call ON, over the hypotenuse, which is 30. Then to find the ON, I just have to times the 30 across to the other side. So 30 times cos 40, which is equal. Excellent, thank you. 22.98 kilometers. Okay, pretty straightforward, right? Now let's see if we can do that using our vectors. So part B, using projection vectors. So what I'm going to do is I'm going to use this formula that's up here. I'm going to be projecting it, because I'm trying to find how far north we've gone. We're going to be projecting that onto the y-axis, which we call the unit vector j. Right, so I'm going to say let j, just as a reminder, be the vector pointing north. So I am taking, I'm going to call this the point P that we're walking out to here. I'm going to project the line OP onto the vector J in the vertical direction. Okay, to write that, I'm going to be finding the length of vector ON by projecting OP onto J, little vector J. So using my formula here that I've written up here on the board for you, what is that going to mean for my symbols? The projection of OP onto J is going to be the length of OP times cos of the angle times by the unit vector J. So, actually I don't need the unit hat on that because it's J. So then I know the length of OP. The length of OP is 30, and I know the theta, which is 40, and I have my vector J there. And so it's really the same thing as what I got before. I have 30 times cos 40, which is the 22.98, and the J vector on the end there is telling me that it is going north. Okay, so we can write a little conclusion for that. Therefore, I have gone 22.98 kilometers north. Okay, so you can see that we're really doing the same thing when I do it with SOHCAHTOA as when I do it with my projection formula. Okay, next one. They're slowly going to get a little bit more complex as we go. Question 2. A ship leaves port and sails on the east side of the northerly direction in a straight line at an angle to the straight north-south coastline. Did I lose anybody yet?
What?
No. Okay, yes, all right, interpretation time. We have a ship out at the ocean. There is a coastline, so your beach, which is on the north-south of your compass. So there is never a beach that has ever been that straight or perfect, but we're going to pretend that our north, there is one?
There is now.
Oh, there is now. There is now. There is a perfectly north-south beach. There it is, my north-south beach. We have a ship that is sailing on the east side, okay, which is why I left the east side clear. My sand is my shaded part. My ship is over there in that nice clear water. And it is traveling in a northerly direction, but when I say northerly, that does not mean directly north. It means it's going up, that's right. So it's going to be traveling, I'm going to draw a thing down here, so I have an origin. It's going to be traveling somewhere out that direction, northerly, away from that coastline. Its speed along the coast is 20 kilometers per hour. So if you were someone observing that boat from the coast, it would look like it was traveling 20 kilometers per hour. I'm going to get rid of my shading now so that I can write that on there. 20 kilometers per hour along that coastline. But its speed in the water, the speed that it's actually traveling at that angle, is 25 kilometers per hour. There is no current. Good, we don't have to take that into consideration. Find its direction of motion and its speed away from the coast. All right, using a velocity resolution diagram. Okay, so let's put some directions in here. I'm going to put an arrow on the end of that one because it's traveling northerly away from my coastline.
What does it mean by northerly away from the coastline? Like, you shouldn't be going straight? No.
Not directly north. It says that it's traveling at
Northerly at north
10 degrees.
89 degrees east.
That's right. Anything that's pointing in generally the up direction is a northerly direction. It's not perfectly
So
north.
anything more than less than 45 degrees?
No, anything less than 90 degrees. Anything above the horizontal line, correct,
Yeah.
is northerly. Anything below the horizontal line would be southerly. Okay, so we are going to be trying to find the speed away from the coast. So that's going to be like my resulting vector in there as I'm coming away from the coastline.
Just made an A.
And we did know that it appeared to be a 20 kilometre per hour vector as we travel along that coastline. So, sorry, what was that?
25 squared minus 20 squared.
Yeah, we're going to get, yes, good. Slow down.
Oh,
Okay. First thing I'm going to do is I want to know the angle in here at which I'm traveling away from that coastline. So I'm going to start with my adjacent and my hypotenuse there. So I'm going to be using cos again. Cos theta equals 20 over 25. And you're going to inverse cos that to the nearest degree. Very good. Then I want to find the distance, as we said, away from the coast. If we're doing this as a velocity vector, so this one, I'm going to put some letters in here. This one's going to be my velocity that I'm currently traveling. And we have a I component, so there's going to be, and a j component. So this one would be 20j as we go in the northerly direction. And the one that I'm trying to find is the one in the I direction, which would be this one over here, but I don't know how far it is. Okay, beautiful. Okay, we're going to put a k in there because that's the one we're trying to find. Don't put, x might be a little bit confusing, but yeah, sure.
Like X.
Yeah, okay. So if we were doing a velocity vector, it would be, for my velocity v that I'm traveling, I have ki in the x direction, and I have a positive 20j in the y direction, right? I just now need to find out what that k is, and I can use Pythagoras' theorem to find it. Or Pythagorean triad. Okay, so I'm going to do a quick little Pythagoras' theorem calculation here. So you've already told me, but we're going to write some working out down. It's going to be k is equal to the square root of 25 squared minus the 20 squared. Okay, and that gives you 15. So that means my velocity vector is going to be v for velocity equals 15I plus 20j. Okay? And we did know that that was at, oh, I should write that in there as well, at north 37 degrees east of my coastline. Yeah, okay. Let's do that same question again. It says using projections. So to do that, I want to try and keep my diagram there on the top of the page for a little bit longer. Maybe I'll shrink it down, a bit more room. Okay, I'm trying to find, well, I have the speed along the coastline as one of my vectors, and I already know that that is 20 kilometers per hour. And I can use that, so I'm going to say speed along coast is going to be equal to the projection of my velocity onto the y-axis, which is j vector. Okay, so the speed along my coast, I actually already know that. The speed along the coastline was 20 kilometers per hour, or as a vector, 20j is equal to the projection formula over here. Let's adjust that for what I've got. I've got projection of v onto I. Does anyone have a try? It's going to be the length of vector v
cos 37 times
cos angle, we're starting again, we don't know the 37 yet, times by the vector j. And this is I'm going to be able to find that angle again using vectors, is what we're doing here. Yes, the j's will cancel out. The length of vector v is 25. So we have 20j, I'll leave it there for now, is equal to 25 cos theta vector j again. Okay, so the vector j's, as Ben indicated, we can get rid of those, and we're just going to be using the scalar part of those formulas to get the cos theta by itself, which would be 20 over 25, and we're back to the same part we had at the beginning of the last question. Inverse cos that, and we get our 37 degrees again.
36.86.
Yeah, nearest degree. Okay, so that using projections can help us find that angle as well. To find the 15 kilometers per hour, we would still need to do the Pythagoras' theorem that we did up above, so I won't do that again. Okay, but we've used the projection part to show that we can get that same result for the angle. Okay, all right, so let's move on. Question 3. We're doing good here. Question 3. Peter and Paul are pulling a large box using ropes. They can never cooperate, and they end up pulling the box in different directions. Peter is pulling east with a force of 60 newtons. So I'm going to draw this over here. Here is my box, and Peter is pulling east. So here's Peter at 60 newtons. Paul is pulling north, so he's going this way, at 80 newtons. That was Paul. Peter and Paul. What great names.
Those are very accurate links.
Sorry, not to scale.
Yeah.
Oh, seriously?
Yeah.
Oh, fine. Let me make it better. There we go. Is that a little bit better? There we go.
0 for that next one.
Not to scale. Okay, all right. So we want to find the resultant force, which means before I start that, it is probably going to be better if I redraw my diagram. My 60 newtons east, I'm going to put that back here. So that's going to be 60 newtons. And Paul is pulling north, but I'm going to move his vector over here so that they can be tail to tip. Like that. Make sure it's longer. Okay, there we go. 80. Is that better? So 80 newtons for Paul. And my resulting vector from the origin out to there, I'm going to call that F, my resulting force. This angle down here, theta, that will be the angle that they end up pulling at.
That's correct.
Which totally makes sense, doesn't it? One's pulling east, one's pulling north. They're going to be doing something in the northeast vicinity. Okay, so let's calculate that. We can use, if we want to know the force as a vector, it's going to be 60 in the I direction plus 80 in the J direction. We can work out the magnitude of the force though, can't we, by doing Pythagoras' theorem? So we'll say, and the length of that force is going to be the square root of 60 squared plus 80 squared, which is,
Another perfect Pythagoras.
which is, that's why I'm waiting for the answer.
3, 4.
No.
10 to the power of 2.
4. No, 3, 4 out. 5. 3, 4,
100 newtons.
5 to the power of 2 multiplied by 4.
Okay. Make it complicated. So it's 100 Newton resultant force. At what angle? We will use our trigonometry. This time we have got the opposite and the adjacent, so we're going to use tan.
I'm going to guess 48.2.
Close, but no. So tan theta equals opposite, which is 80, over adjacent, which is 60. When you inverse tan that, you get 53 degrees. Okay, that is because of where I've drawn the angle, okay, which is going to the horizontal line. If I was going to try and explain my answer, I would probably write that as a bearing from the north though.
37.
Yes, 37. So therefore, the resultant, oh, can't spell resultant. There you go. Force is 100 newtons north, 37 degrees east.
Wait, it's the north. Do we go NN?
NN?
Yes.
No,
Because Newton's north.
no.
Oh.
Let's do the question again with projections. I'm going to rewrite it with, I kind of already did, but I want to just make it clear that we're using those unit vectors. So we're going to have our 60j across our x-axis.
Isn't it I?
Oh, I, yes, I wrote an I but said a j, you're right. And then it'll be 80j this time in the vertical, but I'm writing them tip to tail. And my resulting force there. So if I'm trying to find my resulting force, I could project F onto I, and I would know that that is 60I. I could go the other way, but I'm just using one of the relationships there to get an expression here.
Why don't you project it onto the J?
I could, that's what I'm saying. I could go the other way as well.
What if so you're projecting what you're trying to find out to this thing?
Yeah, because when we're doing these kind of questions, we're using them to find the angle because we already know what the lengths are. We already know the distances. Okay. So we're using the projection formula to find the angle.
What's projection?
The projection is basically the shadow that vector makes onto, for these cases, it's either on the x or the y axis. It doesn't have to be though, you can project onto another sloping vector. So it's the shadow that is cast onto the vector that you're projecting on.
So if you're projecting it onto, let's say, 20i plus 13j, instead of writing vector j at the end, you write 20i plus 13.
Just call it vector k, but call it whatever vector you want it to be, yes. All right, so I'm going to do this onto the x-axis. So I'm going to project vector f, because that's the vector I've got, onto vector I. And that is equal to, when I project onto f onto I, how long is that length?
100.
No. I'm projecting it onto the I axis there. It's the 60i. Yes? So the projection formula for the left-hand side using the formula is going to be the length of vector f times cos of the angle, which is what I'm using the formula to find, times by the vector, the direction that I'm trying to project it on, which is I. And that is equal to 60i. So again, the i's, I don't need them. I'm using them to confirm my angle here. So I know the length of vector f, which I worked out in the previous part was 100 by doing that Pythagoras' theorem. So I had 100 cos theta is equal to 60, and there's my cos theta equals 60 over 100. And then you will inverse cos that. No, it hasn't changed.
Oh, no, Ben, it's not.
Oh. And you get your 53 degrees again. Okay, and again, I won't write the whole thing out again. So that means we've got the same as before using projections. All right, the last one.
Oh my goodness gracious.
A parcel of mass 8 kilograms is resting on a plane inclined at 30 degrees to the horizontal. Okay, so here it is. Don't make this too small because it's going to have a fair bit of detail on this diagram.
Oh, you do like a little horizontal line down that way and down that way and then the one going up that way and that way.
Yeah, I think you're on the right track, but it's really hard with all the waving arms, but yes. Okay, so we have, I'm going to have my parcel P. I'm going to sit it on my line here. So here's my parcel. It has a mass of 8 kilograms, so I'll get to come back to that part. I know that the plane is resting at a 30-degree angle, so that's that angle in there to the horizontal. And it says, what component of the gravitational force is acting on the parcel in the direction down the plane using a diagram of forces? So, because of gravity, that parcel is has a gravity force pulling it down that direction.
9.8, negative 9.8.
That would cause the parcel to want to slide down the plane in that direction. It's not actually sliding though, because it says it's resting, which means that there is another force acting there. What is it going to be? Probably a friction force on the plane to hold it into that spot. Okay, so we have a force acting now. It wants to come down this direction. and we have gravity pulling down this direction. And that means that there will be we need to draw a perpendicular down here
What the heck?
to get our triangle. So the 30 degrees, there is actually two triangles in there working together. If that would be a right angle in there, and so using angle sum of a triangle, it would be 60 degrees up here. Did you see how I did that?
No.
Nope.
Oh, I got it.
You did get it?
Yeah.
Okay, and then using my triangle coming downwards, I use angle sum again, and the 30 degrees actually ends up down there as well. Okay, now I need to kind of introduce some vectors to work with. So I'm going to call this vector going down W for weight. And I know I'm just going to keep this in kilograms for now because it's part C that actually talks about the forces. So we're going to say that that weight is 8 kilograms that is being pulled down there.
Man.
We're going to find the force that is directed down the plane. So I'm going to call that F. And I think we've got enough to go from there. Okay, so if I want to find the length or the magnitude of my force vector there, I can use just trigonometry. I could use the 60 or the 30. Which one do you want to use? 60, all right, so cos of 60 degrees is going to be the adjacent, which is the length of F. It's going to be lengths, okay? It's not the whole vector, just the length of F, over the length of W, which is going to be my 8 kilograms, because I'm not doing directions on those. So that's cos 60 equals length of F over 8. So my length of X is equal to 8 cos 60, which is indeed 4 kilograms. So there is it's an equivalent of 4 kilograms that is being pulled down, wants to be pulled down that plane, but isn't. Part B, what component of the gravitational force is acting on the parcel in the direction down the plane using vectors? Okay, so we want to use vectors to do what we've just done there again. So this is, if I'm trying to find my force direction, I'm going to need a vector in that direction. So I'm going to say that vector K is going to be my vector down the plane. I'll write that in the instructions here. So let K, I'm just introducing another unit vector, be a unit vector, oh, yep, that's all right, down the plane. Okay, I can't use I can't use J because it's a sloping vector. So I'm introducing another type of vector, calling it K. Now, the vector F is going to be equal to the projection of vector W, okay, the one down, vertically down there, onto my unit vector K. Wrap your head around that. Can you see what that is? If I am projecting W, remember these don't always have to work vertically and horizontally, so I'm projecting onto a sloping vector here. If I'm imagining the shadow of this projected onto my unit vector K, it's going to be the length, it's going to be the F. Okay, all right.
What's K?
K is the unit vector on that sloping line.
Okay.
So F is the whole vector, but I just want a unit vector, so I'm calling it K. Okay. K is okay, sorry. All right, so let's put in, if I'm going to project W onto K, that would be the length of W times cos of 60 times by K, the unit vector, and cos, there's my, the length of W is 8, so there's my 8 cos 60 again. which means that I'm going to get my 4 kilograms in the direction of K, which is what we had from before. So interpreting that, that means hence the force down the plane is equivalent to a 4 kilogram weight. Okay, we've been working in kilograms so far. Part B, oh, there's another part B. That should be part C. What is the force in newtons? Okay, so now we finally want to get to a force, which if we know that it's a 4 kilogram weight, we can just use F is equal to ma, Newton's second law. And it's a 4 kilogram weight, and acceleration due to gravity is 9.8, and that is 39.2 newtons down that plane.
Well, shouldn't it be negative 9.8?
No, I'm just saying 9.8 down. So if I say the word down, then I'm kind of saying that that's in the downward direction. Okay, down the plane. That's right, correct. You have to keep it consistent throughout the whole question.
That's why projectile motion graphs look like this instead of that.
Really? Okay.
They like a concave up. So.
Okay, so part C, or should be part D. What frictional force is acting on the parcel in the direction up the plane? Remember at the very beginning we said that that parcel is resting on the plane, and although gravity and the resulting force means that we had that 4 kilogram weight equivalent going down the plane, something was still stopping it, which is the frictional force. If the parcel is stopped, it means the frictional force has to be equal to that force down the plane. Okay, so let's just write that out as an explanation.
39.2 newtons.
Up the plane.
North 60 degrees west. East.
So since the parcel is resting on the plane, that means it is not moving. So the frictional force must be equal, I'm going to put in brackets, but opposite direction, to the force down the plane. Okay, so that means we're going to have our 4 kilogram, if it was in kilograms, or our 39.2 newtons up the plane. And you could give an angle in there, but that's enough information for that one, I think.